那我们开始吧。上次我们开始说是这个基本群。基本群是的Pi1 m, which is the gamma I to m, and after homotopy,同路登站，然后 the multiplication is just given by gamma 0, star gamma 1 is the t 2t is 0 to 1/2, and gamma 1 2t 0 t 1/2. So namely, we have a 2/2, so you just multiply gamma 0 and gamma 1. So therefore, after homotopy, that is equivalent to, so this is the base point. Base point doesn't matter, actually. not so important. That's the so up to homotopy, this is equivalent to this. Namely, so here you can just get rid of smooth out like this. That's the multiplication of G. And then 单位元是 just a constant mass, or just constant. 单位元 is something like this. That is contractible to the point. Contractible. Okay. 同类。然后逆元呢？逆元 inverse 逆元。For instance, this is gamma. Here is gamma. Gamma inverse is something like this one. Gamma. Okay, that's the case. So example, y1 of Rn is what? Tricky, wonderful. Just go. So this is the cursor. So this is cursor contract. Rn 是可塑的contract. So it's a trick. 然后我们上次我们已经看过Pi1 S1. So how many times you wrap? So just S1 is mapped to S1 up to homo. So this is the notation. S1 is mapped to S1. Okay. So that is the mapping degree. So how many times you wrap S1? So therefore this is okay. 然后我们上次最后我们 two point 我们看过这样的例子。So you just get rid of 2 point from the space. Then there's a one generator here. There's another generator here. The orientation, whichever is okay. Okay. Like this. So you can have the how many times you wrap here and how many times you wrap another element. Okay. However, so here AB is not equal to BA. It's you cannot. So AB is something like this one. AB is something. Oh, sorry. AB. Oh. Maybe like this. Okay. AB is something like this. The BA, this is AB. BA is something like BA is something like this one. No, sorry. I told you wrong. So BA is something like this one. BA is something like this. Okay. Something like this. So this is B. And clearly, you cannot move one white to yellow. So AB is something like this one. But you cannot move this path to this yellow because there's a hole here. Okay? You cannot drag this one into the yellow one because there's a hole here and the hole here. So therefore, AB is not equal to BA. Okay, so therefore, this is so it's a non-commutative, non-abelian case, non-abelian group. And then, to show the element in this pi 1 point, and another way to show 2 point, sorry. Another way to show is like this thing. So S1, which S1 is something like this one. S1 is something like this one, and then you just glue them at the one point. So this is called S1 wedge S1. 1 point. So that they are homotopy equivalent. 同路单站，它们同路单站。Okay. And this one is equal to, the people just write the free group, Z cross Z, Z star Z. So this is called free group. So 自由群。So 自由群。So free group means that so one element is A and the other element B, B, A and B, and B, and B. And this is generated by A and B, and that's it, no relation. And then AB square, A cube, A B inverse, A minus 4B cube, and so on. So you just write down that all the multiplication like this. So that's a free group. Okay. Free group. And to show that, so you just have AB. So this is the A, B, but the B, BA. Okay. AB is different from BA. Okay. So that each point, so each intersection corresponding to, so this is ABA. Say this one is BAB, and so on. So there are infinite many like branches. There's an infinite many error, and this is called Kelly graph. Okay. So to show the free group of Z star Z, so you can use Kelly graph to element in element in Z star Z. You can show the Kelly graph, and then each intersection corresponding to the element in Z star Z. So that's a case. How about another example? How about pi 1 of Sn and greater than 1? What is this? Pi 1 Sn. Say it. Trivial. This is trivial. Because if you have a two sphere, whatever map you can have, whatever map you can have, just get rid of the south pole at some point, except which does not lie on this curve, and just get rid of one point, and it becomes R. It's isomorphic to Rn. point is the Rn. And Rn is contractible, right? So this is contractible to point. So therefore, always it's trivial. Yes. When n is greater than. How about this one? Do you remember RP2? So RP2 is the Sn, S2, and you just identify the opposite point. Okay, opposite point, the antipolar point. So therefore, so you just get rid of the southern hemisphere, and then just look at this. And in fact, so this point is identified with this point, the antipolar point. Okay. So therefore, you can have this is in fact the path inside RP2. Okay. I would say it's not only path, it's just a curve. It's not curve. Loop inside a RP2. Okay. However, this guy, if you have one more, okay? If you have one more, then you can just bring it to contractible to the base point. Okay? So it becomes trivial. Do you understand? It becomes trivial. Okay? It becomes trivial. So now this one, so if you have an element A, okay, element A, but A squared is trivial. Okay? So therefore this is called Z2. Or more precisely, people write like this. Z2. Okay. Yeah. Okay. So that's the example. And another example we look at is the pi1 of T2, which is which is commutative. This is, in this case, this is commutative. Appealing. Okay. Yes. And if you have a map from topological space, and in particular is mapped to Y0, okay, then this will induce the map between the fundamental group. So you just have map between some space M to M, like this one. Whatever. Then if you have a map, so the path like this way, if you have a map, this can be just mapped by F. By whatever. can be like this way. So this is the gamma, and this is the gamma dot f. Okay, gamma dot f. So you can just map by two topological spaces. Okay. So this will induce the map. So gamma. Okay, that's the intuition. So the yeah. And if the F0 is equivalent, the homotopy equivalent to F1, homotopy equivalent. So, Tolun, okay, Tolun, then this will induce the same. So this is a homomorphism. So as a group homomorphism, it's just induced the same isomorphic map as a homomorphism. In particular, so the and then the homotopy equivalent. So which means that there exists G n goes to m such that f like this. So the homotopy equivalent, for instance, Rn and then point are homotopy equivalent. Okay, so in this case, the so f Rn goes to point is just any point. Any point is mapped to point, and then inverse is just a point to Rn is just inclusion. Point goes to 0. Okay. Origin. They are homotopy equivalent. It's just contract. Okay. Contract. Okay. In this case, so this will induce. So this the pi1 of n is mapped to f star pi1 of n. Furthermore, G star will induce another morphism. And we already knew that the f star dot G star is identity and identity of pi1 n, and the G star of f star identity of pi1 n. Okay, identity of pi1 n. So therefore, this means that the pi1 n is isomorphic to pi1 n. So that's a homotopy equivalent. And in particular, so here is a homotopy equivalent. So R2 multiple 2 point is homotopy equivalent to the S wedge S. S1 wedge S1. So therefore, it's isomorphic. More precisely, this isomorphic. Any question at this moment? So everything up to homotopy equivalence. But for pi 1, okay. Okay. If the pi 1 of n is trivial, then n is called simply connected. So 这个是单点的单点通的。单点通的。那比如说高位的球面是单点通的，是单点通。Okay. 对，单点通。So another important notion is the covering space. 覆盖空间 not 覆盖复叠空间。复叠空间。Another important notion is covering space. So this one is very difficult to read. DA 空间 ，OK， 复叠空间。So 复叠空间是the following. So x tilde to x is a map is onto surjective or surjective. Onto surjective such that any point P okay inside so there's a so some neighborhood use 领域 neighborhood pi inverse sufficiently small neighborhood pi inverse u is the isomorphic to some bunch of then each copy is homomorphic to U itself. So for instance, example, S1 cross S1, Z is mapped to Zn, like this way. Yeah. So then this one is just if you have S1, you just have any copy, and then you just have like this. Okay, you can just n times you just run S1. Then take the point here, pick a point P here, and then consider the open neighborhood like this U. U here. Okay. U here. And this is a map. Sorry, this is map pi. Okay. It's better not to use pi because I use pi for one of the. Let's see. P. P is not good. P is point. what kind of F? Maybe F. This is F. The preimage of U. Okay, image of U is just these part. Okay, these part. So let's say U1, U2, U3, U4, U5, U6, and so on. And each copy is the homeomorphic to the original one. Okay, each copy is homomorphic to the original one. Okay, is that okay? Yes. So that's the covering space. But if the U is too big, so U is too big. Like if you cover everything, the preimage is everything, right? Preimage is everything. Okay. So then you cannot write down like this bunch of copy of the open neighborhood. It's just that if you pick everything for S1, the preimage is S1 itself. But therefore no longer you have the disjoint union of the same piece. Okay. So this means disjoint union. Okay. So if this is the case, n sheeted covering. So this is 6 sheeted covering. In this case, n n 重复叠n sheet cover. Okay. And in particular, so that is a covering space. In particular, if pi 1 of x tilde is trivial, it's called universal covering.通用复叠。这个是通用复叠。通用复叠。Okay. The example is the R to S1. That is so say this is x is to e to the 2 pi I x. So this is the map. So you have R and 0, 1, 2, 3, -1, -2, -3, and so on. Okay? But each segment here is mapped to S1. Okay? So here is just a S1 mapped to S1 by n shaded. But here it's an infinite many covering from R to S1. Okay? So that each integer point is mapped to 1. It's just 1. It's just mapped to 1. And then each segment is mapped to the S1. And in particular, pi 1 of R is trivial. It's trivial. So therefore, this is universal covering. Moreover, if you look at the preimage of 1, you have an integer, right? You have an integer. So therefore, you can have the pi 1 of S1 is just a group generated by preimage of integer. So if you have bijection, if you have a universal covering, there is a bijection between pi 1 of x and then preimage f inverse of p point. Okay. The projection. So let's pick a point 1 here and look at the preimage. Okay, there's an integer point, right? The point is integer, and we know that the pi 1 of S1 is integer. Okay, this is the bijection. Do you understand what I mean? So that's true because I mean, so if you have S1 is mapped to 1 times, it just corresponds to this one. And if you want to do that twice, you just have it like this way, and so on. So preimage of the point corresponding to integer point, that will count how many times you just wrap. Okay, you just wrap. So therefore, if you have a universal covering, preimage point is just the fundamental one-to-one correspondence between fundamental. So another example, Sn is mapped to Rpn. Okay. So Sn Rpn is just that you just identify antipodal map x and a minus x, and you just identify antipodal map. Okay. So this is a 2-to-1 map. 2-to-1 map. Okay. Just And then if you look at the point here, pointing here, the preimage is just plus minus x. Okay, plus minus x. So therefore, so if you look at the point, pick point here, it's a double cover. It's so double cover. Okay. And moreover, pi 1 of Sn is trivial. Pi 1 of Sn is trivial. Okay. So It's a universal covering. And moreover, universal covering RPN. Moreover, pi 1 of RPN is isomorphic to what? Pi 1 of RPN is isomorphic to what? Z2. And if you look at the pre-image of point, you have a 2 point, right? So there is a bijection between plus minus x. The bijection. 2 point. That's it. So recall that the SU2 as a topological space is isomorphic to what? SU2 is something like this one. Alpha, beta, minus beta bar. Alpha bar. Alpha. Alpha and beta is a complex number. And this is A. So determinant A is equal to 1. So which is equal to alpha squared plus beta squared. Okay. Then topologically what? S3, good. And then how about pi 1 of SO3 is isomorphic to what? Topologically. So this is RP3. And so therefore pi 1 of SO3 is isomorphic to Z2. Okay. And then pi 1 of SU2 is isomorphic to 1. And we know that we already constructed the double covering SO3. It's double covering. Okay. This double covering is very easy to see the following way. So you have the, if you try to rotate this one by 2 pi rotation, my hand is twisted, okay? However, you can add one more 2 pi rotation, like this way, you can come back to original point. Okay. So what's really happening is that so my arm, my shoulder is fixed here, okay? So therefore, it's just constant map. However, my hand is mapped to some loop inside a RP3, RP3, SO3, okay? So then, therefore, my shoulder is just constant map. It's really homotopy. So this is shoulder, my shoulder. And this is my hand. This is my hand. Okay. And this is time. So this is time. Okay. And then if you go to 2 pi, so just so it just shoulder is constant map. So this shoulder is constant map to the RP3. Shoulder is constant map. Here is constant map because it doesn't move. Right? Here it just keeps fixed. But my hand is just rotated by 2 pi. Okay. So that when you do the 2 pi rotation, it's really corresponding to just my hand is just mapped to like this way. Is mapped to. Okay. My hand is just mapped to. My hand is just move this yellow line. Okay. And if you add one more yellow line, it can shrink to the. It can just shrink to the point, right? So the yellow lines, one yellow line and another yellow line, then I can bring back the original point. That you can shrink to the original. So this is yellow line, A, and this is A square. And A square is trivial. It's trivial, but helpful. You can just bring back to original position. So they're really homotopy. So this is non-trivial element in RP3, sorry. And then another non-trivial element is by 4 pi, you go back to the shrinks to the original. It's a constant map. It becomes constant map, right? If I say like a constant like this way, it's just constant. But that is equivalent, the homotopy equivalent to like this. Okay, so that's double covering. So this is called this explanation of double covering from SU2 to SO3 is given by Dirac. Yes. So is there some? Unfortunately, and I forgot to bring the bolt, but this is a Dirac bolt trick. This explanation. Right. So that's that's the notion of this Fourier conjunction. Any question at this moment? Okay. So then, homology. Okay. Homology group can be computed. So if you have the X is some union of U1 and the U2. You can just construct the homology of X by using H star of U1. So there's the may arbitrage in course exact sequence. May arbitrage exact sequence as what? Sorry. Yeah. 数列整合 okay. May I be towards the exact sequence? So this is called序列分值。正和序列 So we already saw that the this kind of map. So if you have X is some union of U1 and U2, then you can have a vector sequence to compute this X itself. Okay. So that's what we saw previously. So that's exact sequence. There is similar split exists in fundamental group on competence theorem. On competence theorem. So that's the, so you just construct. So if X is U1, U2, like this way, then so the assumption is U1, U2, U1 intersects U2 is path connected. Then pi 1 of X is just a free group of pi 1 of U1 and a pi 1 of U2 with up to some normal subgroup generated by as follows. I1 star of omega is the omega is inside of pi 1 of intersection U2, like this. Okay. So normal subgroup generated by like this. I'm not going to explain very detail. I mean, it's kind of cool. I mean, so normal subgroup is just so normal subgroup in G. Usually, normal subgroup G is just normal subgroup is just a group such that N in N and G in G such that the NG G inverse is also inside N. That is normal subgroup. They form a group. So essentially, the normal subgroup generated by this element, you just conjugate by this free group. Conjugate by free group, you will get the normal subgroup. Anyway, so the von Compton theorem is that if you have the total space can be decomposed into the two pieces, one can just construct the fundamental group of total space out of the small subspace, fundamental group of this small subspace. That is a von Compton theorem. It's very similar spirit that may be trusting. This one is also using homology of smaller pieces. One can construct the total homology of total space. In particular, so here, so U1 and U2 are intersections simply connected. Then is isomorphic to pi 1 of U1 free group of two space. So the simplest example of this van Kampen theorem is that the X is S1 wedge S1. So it's just S1 wedge S1 is just S1 is this one, and it just glue them at the one point. So intersection is just point, right? Intersection is 2. So U1 is S1, U2 is S1, and the intersection point. Okay. The intersection point is, of course, the fundamental trivial, but helpful. In this case, pi 1 of S1 wedge S1 is just a V plus V, a free group. So pi over S1 is Z, right? Okay. So that's the simplest application of van Kampen theorem. Any question at this moment? Okay. So if you use this fundamental group, so the Hong conjunction. So sorry, closed. Then so this is a conjecture formulated like around the beginning of 20th century. So 1900. Okay. So it's a very simple statement. So but n is greater than or equal to 5, it's proven by Snell in, I think, 1960 something, by using the H coordinate. It's called H coordinate. Essentially, you use some handle decomposition, and then it's called surgery and so on. It's proven by Snell. Or use moles. So this is his paper is very, very. So there's a book by Milner. It's called H coordinate. So this is the beautiful proof here. N equal to 4, Friedman. And N equal to 3 is parallel. Yeah, I forgot 2000 something, around 2002. By using something called Ricci flow and so on. Friedman theorem is a very using wild topology in 4 dimension. So everything. So and all this conjecture is to be true. It's very simple statement, but it involves very deep mathematics. So that's a Poynting logic. Okay. Any question about fundamental group? So in general, so before So by the way, so I'm going to talk, so SU2 is mapped to SO3. So this is double covering. And usually, so this SON is in fact pi 1 of S1 is in fact Z2. It's Z2, and then in fact it's double covering. It's always called it's called spin group. SON is just a rotational group, but it's always the fundamental Z2, and its universal covering is called spin group. Okay. And then it's related to spinor and so on. Anyway. Okay, so that's a generalization of higher dimensional rotational group. Now, so we'll talk a bit about this 高阶同论群 the higher homotopy group. Okay, so it's called pi n. Okay. So one way to define this 高阶同论群是考虑连续映射alpha. So I is the interval, I to the n, and then such that boundary of In alpha is equal to point. So namely, so you have so I cross I, something like this one, I cross I, but so this part, the boundary of this one is mapped to some point x, xc, x naught. And the other part is mapped to some other place, like this way. Okay, like this. So namely, so this is just that. So and then you just consider the up to homotopy, everything up to homotopy. So therefore, essentially, you just map Sn, essentially this pi n. This one is just group by up to homotopy. Sn is mapped to X. Okay, that's what's going to happen. So you see that if you identify boundary everything, it becomes Sn. Okay, identify the point. This will just become something like this one. It's just the X. Identify all the boundary point to the south pole, and this purple part is just become this part. So therefore it becomes Sn. So it just essentially after homotopy, you just how you map Sn to X. So that's the homotopy group. Okay. So yeah, so therefore pi n of x x naught is essentially the how Sn map to X after homotopy equivalence. Okay. Homotopy equivalence. And then this is always, so n, of course, now I just consider n is greater than 1. Then pi n of x naught is abelian. More precisely, finally generated. That can be just obtained by just the same thing. So that it's just I cross I, but you just map so alpha dot beta is essentially, so you just map so this part is mapped to just the 1 point. The point and this part so so alpha is mapped to like this way, and the beta is mapped to this way, okay. And then this is the alpha, and this is beta. But you can just swap the order. This is I, and this is 1/2, and 0 to 1/2 or something like that, and more. And you can swap the order very easily by just moving this yellow, or shrink a little bit, and then just move to like this way. So everything after homotopy. So you just shrink this yellow and purple region slightly, and just move like this way. Then it's easy to move this way and this way. And then so this is beta times alpha. So therefore it's abelian. It's abelian. Okay. Moreover, it's a finally generated abelian. You can show them. So therefore, so the pi 1 is something like this one. Finally generated abelian group is something like this one, plus the torsion part. Like this. So this is called free part. As far as I know, it's called free part. Yeah. So if you have an R, rank R, free part, and this is called torsion part. Okay. This notation. Gaussian统论就比统调群难得多，难得多。 统调群很容易的，但是这是同论群非常复杂。但是比如说派m Sn where m is less than Sn, or like this way, is the 距今没有完全分类 so for sorry the n. So if this is a case, like for instance, so this one is like a not classified. Not classified. I mean, we already knew H star of Sn. This one is super easy, right? Super easy. Homology group is very easy. Okay. But the homotopy group is very difficult. Homology group we know, right? So this one is C k equal to 0, D k equal to N. The other is just 0, and after that 0, right? So that's the homology group. Okay. But this one is not the fully classified. It's very difficult. Of course, the reason why I wrote like this way is that if pi m, if sorry, what I'm doing is the opposite. So this is very obvious, right? So if you have n-dimensional sphere, if m is smaller than n, so the sphere Sn dimensional sphere is something like that, like this way. And of course, if you put some get rid of point, and it becomes contractible, and everything just shrinks to the point. Okay. Therefore, this is trivial. So I think it's better to the trivial abelian group. Okay, and so if the pi n over Sn is just a z, it's just mapping degree. Okay. How many times you wrap Sn? By Sn. That's the mapping degree. Okay. And then the interesting thing that follows. So interesting thing is the pi 3. Okay. Pi 3 of S2 is in fact related to so-called Hopf vibration. So Hopf vibration is as follows. So the Hopf vibration is S3 mapped to S2. S3 is something like this way. such that the okay. So S2 is in fact the same as CP1. Okay, CP1. So CP1 is in fact the optimization sphere mode phases. So CP1 is essentially Z1, Z2 is equivalent to E to the I lambda Z1 and E to the I lambda Z2. Okay, so that's a CP1. So you just identify the phase up to phase equivalence. You just identify the optimization sphere like this way up to phase equivalence. So that's a CP1. Okay. CP1 is isomorphic to S2, so there is a map from S3 to S2. Okay. And if you look at the point here, and of course after this identification, I just write down the equivalence class is Z1, Z2, like this. This is the standard notation of CP1. If you look at the preimage, it's just a phase. It's just phase. So therefore, it's just a preimage. It's just a S1. So it's called S1 bundle over S2. It becomes S1 bundles. This is called Hopf vibration. So this is called Hopf vibration, and it's related to, so that later we will introduce so-called connection and so on to the, how to say, vector bundle or principal G bundle, but this is related to so-called Dirac magnetic monopole. Okay, and then Dirac monopole is related to Chenley, Chern class and so on. But before going that, so you can just construct a map from S3 to S2. Okay, and then so if you look at the so this. Let's call this H. The map is H. So there is S3. So if you look at the preimage of south north pole, it becomes circle. Okay. So this is preimage of north pole of S2. North pole in S2. So it's so since we identify the phase rotation, all the S3 inside S3, you just identify the phase rotation. So this phase is in fact this phase rotation of the north pole in S2 inside S3. And if you look at the preimage of the south pole, you get another circle. So H, south pole, okay. Another circle. And then they link together inside S3. Okay. Link together. And this linking number is equal to, in fact, this linking number is in fact H inverse of N, and the H inverse of S is equal to 1. Okay. It becomes H equal to 1. And so therefore, so this is called Hopf link. This is called Hopf link. Because I mean, it's just that we can construct this link by using this Hopf vibration. We just look at the pre-image of North Pole and South Pole in S2, and then looking at how this fiber look like. Then they just intersect together. Okay. So likewise, if you have the map from S3 to S2, so if you have a map from S3 to S2, okay, and then looking at the pick up 2 point, North Pole and the South Pole in S2, and looking at the pre-image of the North Pole is essentially a bunch of disjoint union of circle. Okay. And then, if you look at so this is F inverse, and then South Pole, so this is the F inverse of South Pole, and looking at how they link together. Okay. So this linking number of F inverse of N and the F inverse of South is called Hopf invariant. Its linking number is called Hopf invariant, and then inside of C. And in fact, this Z will generate the pi 3 of S2 is Z. So this C and C are equivalent. So, and then, so this is generated by the Hopf vibration. Okay. So that's the one thing one can consider. Any question at this moment? This Hopf vibration is very important. And you can consider the same thing as follows. Okay. Not sure. So you can also consider the following thing: pi 2n minus 1 Sn. 2n. It's a higher dimensional version. Where n equal to 2, so you just have this one. This is infinity. N equal to 2, you have a higher, we can consider higher half invariant. In fact, so if you have Sn, 2n minus 1 to Sn, so pre-image is in fact, pre-image is, so pick a point here. So F, the pre-image is the F inverse of P. Is which dimensional manifold? Which dimensional manifold? Which n minus 1? Because 2n minus 1 minus n is n minus 1, right? Is it okay? And then we can do the same thing. Pick north pole and south pole, both n minus 1 dimensional manifold. Okay, inside S 2n minus 1. Okay, so therefore, if you add them up, 2n minus 2. Okay. So therefore, you can consider linking number inside here. Okay. Because in 2n minus 1 sphere, inside 2n minus 1 sphere, one can also, so essentially F inverse of n is bunch of disjoint union of Sn minus 1, both Sn minus 1. And then inside 2n minus 1 dimensional sphere, you can consider again linking like we considered in the S3, inside S3. So this is for higher half invariant. So this is called higher half invariant. And in fact, you can show that this linking of F inverse of n and the F inverse of south pole is minus 1 to the n, thinking of F inverse of south and the F inverse of n. Okay. So therefore, half invariant is 0 when n is equal to odd. Because it has to be, because linking number is the if you swap them together, if you swap them, you get a sign, which means it has to be 0. So n is even, you can get the non-trivial half number. So there's a Hopf vibration. So proposition. for Z3. The construction is the same. So the map is Z1, Z2 is mapped to the Z1 and the Z2. Where Zi is that here is the complex number, and then this is the coordinate number, and then Zi is the octanion. So of course they satisfy and this one is just identified as CP1. And this one is identified HP1. This one is identified octanion P1. Okay. So H is the quaternion. You know quaternion, right? So whatever. 1 A2I plus A3J plus A4K, like this one. And IJK satisfy this octanion relation. And then you can consider the same thing, similar construction. So instead of C, you use H for field or octanion for field, and you can consider similar construction for projected spaces. So you just, this is essentially S1 bundle, or this is S3 bundle. Because the norm of this one, the phase rotation will give you a 3 rotation. This is the S7. Those Hopf vibration always have a linking number. The pre-image of south and north pole has a link by 1, like this, like this. Okay. And then this is the different only. So this higher Hopf invariance is equal to 1 only for Hopf vibration. Only for Hopf vibration. And then so other even n. So Hopf invariance is 0 if n is odd. So therefore n is even to n. So then if you plug it in here, so S4m minus 1 is mapped to S2m. And this is f. And the minimum of Hopf invariant f is in factor 2 for other. Except Hopf vibration n is equal to so that's the case. And then moreover pi 4n minus 1 S2n is the generator is Z. Is given by Z. So I just give a proof of this, just construction of this F by the following. So you just consider S 2m minus 1, 4m minus 1 by just S for m, 2m, sorry. So you just construct like this. And then I think it's better to skip a proof, but so for instance, when m is equal to 1, you can have the following thing. So one is this. So here is m equal to 1 is just s1 times d2. So that is solid torus. It's d1 is here, d2 times s1, right? S1. Okay. D2 times S1. And also, you can have another solid torus. So this is D2 times S1. And you just identify this circle by this circle. And this circle by this circle. And then glue them together. So this is the S1, non-trivial one, but if you just identify D2, it just shrinks to the point, right? You can, and this purple one, S1, is non-trivial inside of this solid torus, non-trivial fundamental group. But if you identify this purple, it's just the inside, it's a boundary of this, so you can shrink to the point. Okay? So everything, so that if you identify them together, the boundary like this way, this will become S3. It becomes S3. Okay? So, of course, the fundamental group of S3 is trivial. So therefore, this purple one, it just shrinks to the point. This green one also shrinks to the point, and everything becomes trivial, and it becomes S3. We have a higher dimensional version of this one. Higher dimensional version of this construction. And if you use that, one can construct the minimum map from map from S4n minus 1 to S2m. If you use this construction, you can just construct half invariance, which is equal to 2. The detailed proof is written in my notes, in the new lecture note. At the overleaf, you can just take a look. I'm not going to go into the detail. So that's the case. Sorry, today I just didn't take any break. Sorry, I think it's better to take a break. Sorry, I was just too much into the lecture. Sorry. Let's take a break. After that, I will show one table, which is called a stable homotopy group, which is kind of an interesting thing. Then, after, yeah, let's take a break. Sorry. So. Wonderful. Okay, shall we resume? Okay, so then, as I mentioned, this is a higher homotopy group. Homotopy group is the really difficult to study, but there's an interesting thing going on. So here is the table I just show pi n plus k Sn. Okay, so that's a notation. Those are table. Of course, when k equal to 0, this k equal to 0, this red one is just that pi n. The pi n Sn is, so this is mapping degree. So that's a z. These red z are the this just a mapping degree, the same n. So blue z are the Hopf invariants. So blue z are really these are this one. Hopf invariants, higher Hopf invariants. Say when m equal to 1, sorry, yeah, m equal to 1, this one, m equal to 2, this one, m equal to 3, this one, m equal to 4, m equal to 5, and so on. These are really Hopf invariant. Is a Hopf invariant, the one I mentioned just previously. The other, if you look at the other, all the finite group is torsion part. The interesting thing is that when you set the n is very big, so n is sufficiently big. Okay, if you set the n is sufficiently big, okay, everything becomes stabilized. Everything d. Unfortunately, in the node, the stabilized part becomes like a gray, but unfortunately, this light doesn't work. Anyway, so when you increase the n, so everything becomes stabilized. Even though the previous around here is kind of messy and they're not equivalent, but if you increase the n, so it will stabilize. So when you set limit n is, so you can just consider it's a stable homotopy group. You can just consider something called stable homotopy group, which is the K. Okay, like this. So in this case, pi 1 stable group is Z2, pi 2 stable group is Z2, and pi 3 stable group is Z24, and 0, Z2, Z240, and so on. Okay, and then this one is known up to K is like around 90. No, K is 90. And the higher K is open problem. But for the computation around here is very difficult. Okay, very difficult when you increase the K. But stable homotopy group is relatively easier. Okay, relatively easier. So the algebraic topologist, one of the very famous in even Fudan, there's one very famous guy working on this stable homotopy group. But is one of the main research topic is this how to compute this stable homotopy group, and it's not a simple way to do that. There is a so-called Adams spectral sequence and so on, and then And then in my note, I explained why they stabilize when you increase the n. I explained in the note, but I'm not going to explain in the lecture. So, but if you're interested, you can read why it stabilizes n when you increase the n. Okay. Yes. So that's the stable homotopy group. Okay. And then so here, so this one is actually pi 4 of S3. Pi 4 of S3. And then also pi 4 of SU2. And this is Z. Z2, sorry, Z2. Z2. Okay, and this is related to so-called Witten's anomaly. SU2 anomaly. The statement is that the, okay, let me brief. Statement is that the, so if you use a gauge transformation, suppose you consider the following the non-abelian gauge theory, SU2 gauge theory, and with Carl Fermat psi in representation R, and then if you use a gauge transformation of this path integral, okay, path integral, you will get the this transformation. This gauge transformation I will explain in Yamil's part, so that's why I just to be very brief. And in fact, so this measure, path integral measure psi and psi bar, get the phase when you do this gauge transformation G. And in fact, this G is just mapped from this space-time R4 to the SU2 gauge group, and then which is the element of this pi 4 of SU2, pi 4 of SU2. Okay, and then if the odd number of fermion, wild fermion exists, you get the non-trivial element of Z2. Okay, Z2. So therefore, the path integral is not invariant under the gauge transformation. You get the sign, minus sign. Okay, you get the minus sign. So therefore, you get the theory become anomalous, and which is called Witten's global anomaly. So you cannot have the odd number of wild fermions in the representation, double representation in case SU2 in the space-time in 1+3 dimension. That is the one example how the homotopy group appear in physics. So that's called the global Witten. So you cannot have the odd number. So odd number, sorry. It's better to explain here. So this measure gets under the gauge transformation. This measure is get the sign if you have an odd number of wild fermions. So therefore, in 3+1 dimension, you cannot have the odd number of the wild fermion. So that's it. And then another instance that appeared so pi1 of m is related to vortices anything. So that's not. So as I mentioned, so the pi 3 of S2, so another instance of pi 3 of S2. So this is again, so the generated by Hopf vibration, Z, and this is related to magnetic monopole. So that's another instance how the pi 3 is related to homotopy group is related to physics. And so and also nowadays condensed matter people just consider like Witten's anomaly. So this anomaly, and then is closer to this higher homotopy. In condensed matter physics, also many people use the homotopy group to study the anomaly in condensed matter physics. That's the the originally, so this homotopy group and so on, like people introduced like a Quillen and Sullivan just purely mathematical reasons, and somehow they are become useful even studying in physics. Okay. Any questions so far? So we study algebraic topology. So topu 代数学。And then let's topu 学 topology. Algebraic topology. So what we have learned is the so far homology and the cohomology. Another thing, fundamental group. And the homotopy group. Okay. Also, we learn so-called up to homotopy equivalence. Okay, homotopy equivalence. So those are the notion introduced by Poincare. And later it becomes much more rigorous and then interesting. So the important notion is this homotopy equivalence, in fact. Homotopy equivalence. And all the invariants are constructed after homotopy equivalence. And then from here, one can construct, so-called construct the, of course, Euler characteristic or a Xu Xin Xu. Euler characteristic, Xu Xin Xu. You can rigorously define for even higher rank. And also from here, the intersection number or linking number, and then cycle linking number, and then those are related to whatever. Biot-Savart theorem, also abelian transform. Those are what we have shown, and also here you just want the Poincare theorem, or like a left-hand fixed point things. Fixed point. So those are algebraic topology we learned so far. Okay, so what we have learned is that essentially the concept of manifold, differential forms, linear geometry, and also simplex geometry, algebraic topology. So far, the basic, very basic. And from now on, we will move on to the notion of the Lie group and the Lie algebra. From there, we will call the so-called vector bundle, and also principal G bundle bundles. So from here, those are very closely related to so-called Yarmel theorem. Those are what we are going to introduce. Okay. So last half an hour, I will explain about the Lie, basic of Lie group and Lie algebra. Any question at this moment? Let me check. So this semester is kind of relatively short, in fact, than the ordinary year. So what's left is 18. 3 more lectures left, except today. So my understanding is the 0615 is a final exam. Is it okay? Is it true? Can you check? Is it correct? Okay. 06. So what's left is today is the 18. So 25. What's left is the 0525 and 0606. Like this one. Yeah. 3 more lectures left. So what I'm going to cover is here little bit the Lie group, Lie group, issue, little bit, and here. So I already talk about the Shannon. And then also here, so here I just talk about a bit about principal G bundle, and the connection. Okay. And the final, hopefully we can talk about a little bit the so-called characteristic classes. Classes which is like a Chen-Lei, and so Pontryagin Lei, also. That's the plan of this the rest of the lecture. Is there any question? I think this time I don't know why. So usually only like 13 lectures in this semester. Usually 14 or 15 lectures we will have, but somehow this semester, maybe because of the changes like kind of late, right, this year, and also it somehow overlap the holidays and so on. Only 13 lectures, so that's the point.那我们开始利群的。So 利群 is the 统计主要群结果和光滑流行的结果的数学对象。对象。So G is a smooth manifold. G itself smooth manifold, but there's a modification. And then inverse. There's a map, smooth map. Inverse, like this. Okay. So that's so the group structure. You have a group structure. 主要群的结构不是结构和对光滑流行的结构。And also, if you have this multiplication rule, you have it's called做平移left translation. So LH. So just map the G to HG. And right translation. G to GH. And then those were the depend open as a manifold. Okay, that's the depend open as a manifold. Now wave统配 wave 统配做平移和右平移是自行的微分统配。我们然后我们学习例子。So 最基本的例子是一般线性群 GL and or GL and C, whichever. So A or C. It's just n by n matrix, and the determinant A is not 0. Okay. So一般线性群 why the determinant A is not equal to 0 is important? Yeah, you need a inverse. Okay, you need an inverse. So, what's the dimension of this manifold? What's the dimension of this manifold? If R n squared, if C, what is the dimension? If C, what is the dimension? Okay. So note that because it's n by n, so you just have count the entry, right? So entry. So those entry, we just look at the entry. So those are dimensions, but so determinant equal to a equal to 0. Then zero locus is codimension element, codimension 1. Codimension 1. So in the case of R, it's a codimension 1. In the case of C, it's codimension 2. Okay. So you just each entry is just R to the n square, and there is a codimension element you need to get rid of. That's a manifold structure. Another thing is that SL and R or C is the same thing. Such that determinant A is equal to 1. What is the dimension? What is the dimension? Good, n squared minus 1, because it's just codimension 1 of this. And how about C? What is it? Good, 2n squared minus 2. So that's a special linear. 特殊线性群，特殊线性群。It's a special linear group. So ON is the same thing, but the real. So that's the same thing, but except real. And then AT is equal to 1. Okay. Which means determinant A is equal to 1. Plus minus. Okay. What is the dimension of this manifold? What is the dimension of this manifold? Okay, first of all, so this means that the two connected components. Okay. So dimension of this manifold. Okay, maybe, yeah, of course, from here you can say something about the dimensional manifold. Okay, maybe we can consider that later. Because linearized version is very easy. That's an SO. 这个是orthogonal group. It's orthogonal, special orthogonal. Orthogonal, special orthogonal. 正交群，正交群 ，and 特殊正交群。Okay, and then the other is unitary group, 有群，哇，有群。Unitary group, and now a dagger is equal to 1. Okay. Okay. So this means that the determinant of A is equal to what? No. Wow. You include the plus minus 1. Yeah. So the or e to the isolator. Mm. 特殊有群有群 is UN. Is everything same? But the determinant A is equal to 1. Okay. That's 特殊。Symplectic we already saw in the this A is inside M to N R is equal to J, where J is 1, 0, 0, 1. Okay. Okay. So that's the thing. 新群矩阵。性矩阵。Okay. The reason why I didn't write that dimension is that it's easy to go to the. It's easy to see that the dimension by looking at tangent space. Okay. It's easy to see tangent space. So it's a manifold. Okay, maybe we can do the following thing. Okay, so let's do a computation. So what's the dimension of this thing? So how many relations you will obtain from here? So dimension is essentially n squared minus number of relations. Okay? How many relations do you get from here? N squared is, of course, the number of entries. It's n by n matrix, number of entry. Okay? But A times A transpose is equal to 1. How many iteration you get? Would you get? So this A matrix times A transpose is equal to 1, 1, 0, 0, 0, like this one. Okay? But this one, if you do the transpose, you get the same relation. Okay? Therefore, this relation obtained from here and this relation obtained from here is the same. Okay? So, in total, the independence relation is this purple direction, purple one. How many of them do? How many relation do you have in that case? Right? And if you do that, this computation n minus 1 over 2. That's the dimension. And then SON is one of the component. SON is one component. Let's look at the UN. Okay. So here, dimension is 2 times n squared. The same thing happened. And now transpose. Not transpose, it's dagger. Okay? The same thing happened. What's going to happen is that the so this green part is the same as green part. Okay. So green part, the relation is the n times n minus 1 over 2 times 2 because it's complex. Okay. However, the diagonal one is always, if you do the A times A dagger, diagonal one is always the real, right? Always real, okay? Because it's dagger, so it's just do the complex conjugate and transpose, right? And then if you diagonal one, it's always have the same thing, so same row or same column. So therefore, only what you get is the real relation. Only if you multiply the A and A dagger, and the diagonal is always real. Okay, so you have an relation. So if you do that, this is equal to n squared. So therefore, 2n squared is equal to n squared. Is it okay? So that's a U. And then SUN is dimension is what? Dimension is what? SUN U is n squared, then SUN is what? SUN, you just add the determinant is equal to A equal to 1. Good. Since unitary group, the determinant is just phase, S1. So you just remove that. 自由性，自由度. Good. So that's what's going to happen. And symplectic. What's the dimension? What's the dimension? How many relations do you get from the symplectic? So let's write down. Alpha the gamma delta part. Anybody any matrix? So A dagger J A transpose. So alpha transpose, gamma transpose, beta transpose. Okay. And then so you have -1, 0, 1, 0 alpha delta beta gamma is equal to -1, 0, 1, 0, right? Okay. And then do the computation, you have a gamma delta, and then you have minus alpha minus beta, and times alpha gamma transpose, beta transpose, delta transpose is equal to 0, 1, minus 1, 0, like this way. Okay. And then you have alpha transpose gamma minus gamma transpose alpha, that's entry, and alpha transpose delta minus gamma transpose beta, beta transpose gamma minus delta transpose alpha. Okay. Transpose alpha, and the last element is alpha beta transpose delta minus delta transpose alpha beta. So those are the relation. Is equal to 0, 1, minus 1, 0. Is it okay? Am I doing correct calculation? Is it so far so good? If I make a mistake, please let me know. Now, how many iterations do you get? Huh? How many relations do you get? So on the diagonal part is what?
Same relation.
On the diagonal, same relation. It's just transpose, but here, yeah, transpose, yeah, that's true. And then you get the minus sign. Okay, so then this one and this one is the they're always
Always zero.
they're always zero in the diagonal part. That's true.
So the relation.
Good. So the relation is the n minus 1, 2 times 2 from here to here. And how about here? How many relation do you get? I think n square, right? Plus n square. And in total you have 2n square. Okay. So this is 4n square minus the 2n square minus n. Is it correct? And this is equal to 2n square plus n. So and let's check my calculation is correct. Let's check my calculation is correct. What is the dimension of symplectic group? Yeah, it's correct. Good. Wonderful. Fine. Now, so this is the Lie group. So it's a manifold. Okay? It's a manifold, but there's a identity element, but you can consider the tangent space, which is German frac G. And then G is the vector space, and this is a vector space. Because it's 且空间在 identity element 的解空间So identity element 的恒定人 in Chinese. Is it correct? How to say identity element in in Chinese? 单位元 Okay. And we know the vector tangent vector, you can introduce the Lie bracket, okay, in tangent vector. And this is called Lie algebra. Okay. So algebra needs to have a multiplication and addition. Addition comes from vector space, and multiplication comes from this Lie bracket. Okay. So, and they satisfy so this one satisfies. Oh my goodness. Okay, bilinear, anti-symmetric, and then Jacobi identity. Okay, Jacobi identity. Anyway, so that's that case. OK， 的例子是上次我们介绍做的例子。Let's stop here.
什么可以擦黑板吗？
啊，可以谢谢。那你还是什么？